This is the first section on chapter 6 on integration techniques, and here we're going to be looking at the reduction formula. Well, this sort of comes from integration by parts that you would have learned in core 2. I'll put a link in the description. And integration by parts basically says that if you want to integrate a product, and we'll call that product u dv dx, then the integral of that product is u times v minus the integral of v du dx. So we know that we're looking for a product where we're going to differentiate one part, that will be u, and we'll integrate the other part, dv dx, to give us v. Now, when we do this, every time that we integrate or use integration by parts, we should end up with a simpler expression, and then this thing that we have over here is easier to integrate. So the types of things you might use in pure 2 when you do this might be, let's say for example, integrating x sine x, where you'd make x equal to u and sine x equal to dv dx. It might be something like even x log x. So in something like this, this is the exception to the rule. We'll make this u, because then when we find du dx, that's 1 over x, and we'll make this equal to dv dx. And the most you'd be expected to use integration by parts is twice. So if we had something like this, then we would use integration by parts, I'll just put IPP, 2 times, because the first time we use it, it will reduce this to something where we've got x, maybe x cos x, something like that. And that we would then use integration by parts again to reduce this down to something like sine x or cos x. So the most we'd be expected to use integration by parts in pure 2 is 2 times. But what if we get something like this? So what do we do in this example where I might be integrating x to the power 7 cos x? Do I really want to use integration by parts 7 times? Well, the answer is no. Or if I wanted to find, generally, if I had something like this, x to the n ex, and I wanted to integrate that, do I do integration by parts n times? Well, the answer is going to be no. We're not going to do it n times. So this is where the reduction formula comes in. It's like a recurrence relation, iteration, where basically we're going to use integration by parts, and then we're going to look at this part here, and it may be written in terms of the original integral. Okay, so let's now look at the reduction formula or formulae. So we would normally have some sort of integral that we'll call in. So this is going to be an integral that has n in it. So it might be x to the power n e to the x. It might be sine to the power n, or cos to the power n, or tanh to the power n. So it may be a normal trigonomic ratio. It may be a hyperbolic ratio that we're talking about. And in these types of questions where we've got an integral that's to the power n, there are 2 types. There's one type where we can just use integration by parts straight, and the same rules follow as for normal integration by parts, is that the bit that has the power n, or the x part, is what we're going to make u. There may be other cases where we need to use some sort of trig or hyperbolic identity, and that's going to be the route that we take. So either integration by parts or trig or hyperbolic identity, it all depends on the question. And then when we use this reduction, or when we write a reduction formula, we're going to end up with something like in equals some sort of function of maybe in minus 1 or in minus 2, something like that. It's going to be some sort of function of a like a slightly different integral. So rather than n, we'll have maybe n minus 1 or n minus 2. But you'll see this as we go through the examples. Okay, so we've been given that I sub n equals this, where n is a positive integer, and we've got a reduction formula to derive in part A, and part B we're going to use that reduction formula to calculate this. Now without the reduction formula we would have to use integration by parts 4 times. Now just a little note before we get started, and that is this. We've been told that I sub n equals the integral of x to the power n e to the x. So for example, that also means that I sub n minus 1 is equal to the integral of x to the power n minus 1 e to the x. Or I could have I sub n minus 6 would be equal to the integral of x to the power n minus 6 e to the x dx. So n can be any positive integer, and I can take away a positive integer or take away an integer from this positive integer, and all I do is change any n's I have over this side as well, which happens to be the power. So what have we got? I to the n equals integral of x to the n e to the x. Now you would integrate this by using integration by parts, and we're going to do the same thing. And if we're using integration by parts, you would make u equal to the x part, x to the power n, and we'd make dv dx equal to e to the x. So we differentiate the u part and get n times x to the power n minus 1, and we integrate the dv x part, and we'll get e to the x. So applying that into the integration by parts formula, then we can say in, which is the integral, is equal to uv, so that's x to the n e to the power x, minus the integral of v du dx, which is e to the x times n x to the power n minus 1 dx. Now if I take this constant over to this side and just write this the other way around, you'll see what happens. So I'll have I sub n equals x to the power n e to the power x minus n times the integral of x to the power n minus 1 e to the x dx. Now this part here is like this part here, but with n minus 1. So this part, this integral, the whole integral here, is equal to I sub n minus 1. So instead of writing that integral in yellow, I could write this is equal to this. So that's what we're going to do. So I sub n is equal to x to the power n e to the x minus n times I sub n minus 1. Now have a look. That's what we needed to prove, so we can just put as required. Now when we move on to part B, we're using this reduction formula here, so it might be worth highlighting it so we can see what we're using to work out this integral here, x to the power 4, because we don't want to use integration by parts 4 times. Well, we could, but it would take us about half an hour to do so. So the integral of x to the power 4 e to the x dx, well, that's actually equal to I sub 4. So we can use the reduction formula to work out I sub 4, and the reduction formula is up here. So I sub 4 is x to the power 4 e to the x minus 4 I to the 3. Now what do? It's called a reduction formula because it reduces. So we're going to work out what I sub 3 is. Now I sub 3 is equal to I3, or I3 equals, so just replace n with 3, x cubed e to the x minus 3I sub 2. Do the same thing again. We want to work out I sub 2. So it's going to be n equals 2. Now with n equals 2, I sub 2 is equal to x squared e to the x minus 2 I sub 1. And we can do the same thing again. We want to keep reducing it until we get something that's easy to integrate. We don't want to have to actually use integration by parts at all. So I sub 1 is equal to x to the power 1 e to the x minus 1 times I sub 0. Now what is I sub 0? Well, that's when n is 0. And I sub 0 would be this integral, integrating x to the power 0 e to the x, which is just integrating e to the x, which is just e to the x. So where we have I sub 0, I can just put e to the x. Now, the rest of the question is algebraic. We need to take care because now we need to sort of substitute. So substitute e to the x here. Then substitute I to the 1 with this. Then substitute I sub 2, not I to the 1, but I sub 1. Then substitute I sub 2 with this. And we're going to keep substituting. So this is where we need to be careful. So I sub 4 is equal to x to the power 4 e to the x minus 4 times I sub 3. And what was that? It was x cubed e to the x minus 3 I sub 2. And what was I sub 2? So we'll put some brackets in. X squared e to the x minus 2 I sub 1. And what was I sub 1? That was x e to the x minus I sub 0. And what was I sub 0? That was e to the x. So all of that question just became a very simple integration, and the rest was just substituting using this reduction formula. That's where it becomes useful, because we don't have to use integration by parts 4 times, because the pattern. And this reduction formula, this recurrence relation that we have here, has that pattern embedded into it. Right, so let's now start expanding the brackets. And I'm going to start by expanding the inner brackets here. I don't want to make any mistakes. So I sub 4 equals x to the 4 e to the x minus 4 times by x cubed e to the x minus 3 x squared e to the x minus, and we'll expand these brackets, 2x or minus 2 x e to the x plus 2 e to the x. And then we can expand the next set of brackets, so we'll multiply everything in here by negative 3. So I sub 4 equals x to the 4 e to the x minus 4 times by x cubed e to the x minus 3x squared e to the x plus 6 x e to the x minus 6 e to the x. Okay, and then we just got one set of brackets to expand. Now notice there's nothing to simplify. We've got things here in descending powers of x. So our final answer, I sub 4 is x to the power 4 e to the x minus 4x cubed e to the x plus 12 x squared e to the x minus 24 x e to the x plus 24 e to the x. So all done without having to use integration by parts, and I mustn't forget my plus c on the end. So let's just highlight that answer here before we move on. Okay, so this question here, it shows that if I sub n equals this, then we need to show that this reduction formula, this recurrence relation is true. But notice this isn't a product this time. There's no x to the power n. So what do we do here? Well, we're going to split this up into a product of sine to the power something times psi to the power something. But what power? Well, the clue is here. This is the clue. Yeah, because if you think about it, if I was to use integration by parts, this might be like the UV part, and then this part here would be integrating something again. So here's the clue, because this would sort of match up with the UV part. So we're going to write sine to the power n, like this, sine to the power nx as sine to the power n minus 1 x, that's the clue that's given because we see it there, times by sine x. And the bit with the power is always the part that we make u. So this is going to be u, and this part here will be the dv dx. Okay, so I sub n is equal to the integral of sine to the power n, and that is equal to the integral of sine to the power n minus 1 times by sine x. So we're going to use integration by parts. So we will have u equal to the bit that's got the power, sine to the power n minus 1 x, and dv dx is going to be the sine x. So du dx, I'm just going to use the chain rule. Now if we think of this as sine x to the power n minus 1, so we can write it like that, using the chain rule we'll get n minus 1, so you differentiate out the outside, which means then this power becomes n minus 2. Inside of the bracket doesn't change, and we multiplied by the inside differentiated, which is cos x, and then v, if we integrate sine, we get negative cos x. Okay, so our integral is going to be using integration by parts uv, so it'll be minus sine to the power n minus 1x times by cos x. So that's our u times by v, and then v du dx, so minus the integral of this times by this. I'll simplify in a moment, but I'll write the whole thing out. So I'll have n minus 1, and that's times by sine to the power n minus 2 x, mustn't forget the x, and that's times by cos x, which is in turn times by v, which is negative cos x dx. Okay, so let's tidy this up, because well, this will stay the same, minus sine n minus 1 x cos x. Yeah, it will simplify because we're going to have cos squared, the negative we can bring over, and the constant, so you can write that as plus n minus 1, so there's a constant taken over, there's a constant here, and this will be sine to the power n minus 2x times by cos squared x dx. Now you'll notice that actually this sort of part sort of matches up, but here we need to have this I sub n minus 2. We've got that, so we need to get rid of that cos squared, so we can use the identity and change that cos squared to 1 minus sine squared. So we'll do that and write down what we get when we make that substitution. So I sub n, negative sine n minus 1 cos x plus n minus 1, and integral of sine n minus 2x, and then 1 minus sine squared x. Now we'll multiply out these brackets here. So we're just using a trig identity to get it into the form that we're interested in. So that will be integrating sine to the power n minus 2x. Then if I multiply this with sine squared, effectively adding 2 to the power, it becomes sine power nx. Now we know that we can write these integrals separately, so that'd be sine to the power n minus 2x dx minus sine to the power n dx. Well, because we can write them out separately, we might see actually, well, this part here, that's the same as I sub n minus 2. Yeah, if you just replace n with n minus 2, you get this. And this part here is the same as I sub n, which is what we started with. So we're going to make those substitutions. So I sub n equals this. And now what we can do is say, right, I sub n minus 2 and I sub n here, like that. Now we'll expand the brackets. So we'll now have this minus sine power n minus 1x cos x, and then plus n I sub n minus 2 minus n I sub n, and then we've got minus I sub n minus 2 and plus an I sub n. Okay, we're almost there. So the next step, what we're going to do is, I'll notice I've got I n on both sides, I sub n, so I can take that away. So that will leave this, and I'll take this across the other side, n times I sub n, and I will get negative cos, negative sine to the power n minus 1x cos x, plus, and then I'm going to refactorize the I sub n minus 2 because of this here, and I can refactorize that and do n minus 1 I sub n minus 2, and then the last step is just to divide both sides by n, and I will get this I sub n equals negative 1 over n sine, I keep writing cos, it's sine n minus 1 x cos x, and then the n plus 1 or n minus 1, divide that by n as well, I sub n minus 2. So we get what they want as required. So just write that down as required, and then we'll move on to part B. Okay, so part B says apply the reduction formula found in part A, which is this, and then work out this sine to the power 4x. So we're just going to create a bit of space at the top and do part B. Right, so this here should be fairly straightforward because it's just substituting numbers in, and actually we're going to be substituting n equals 4 because we've got sine to the power 4x. So n equals 4 into the reduction formula gives I sub 4 equals a quarter sine cubed n minus 1, 4 minus 1 is 3, cos x, plus, and that will be n minus 1, 3 over 4, I sub, now this is going to be 4 minus 2, so it'll be I sub 2. Okay, now we've got a choice here. Since I sub 2 is going to be integrating sine squared x, that's something that's easy enough to integrate because we can replace sine squared using a double angle for cos 2x. Cos 2x is 1 minus 2 sine squared x. So if we rearrange that, we can say actually I2 is equal to integrating, let's see if we rearrange it, so it'll be a half minus a half cos 2x. So that's something that we can integrate. Or we may say, right, let's now work out what I sub 2 is, and then we'll get I sub 0. I'll show you what I mean. So this is an option. So we might say, instead, we'll say, okay, let's work out what I sub 2 is equal to, if we didn't fancy trying to integrate sine squared. So if we do that, let's see what happens. So I sub 2 is going to be equal to, using the reduction formula, negative a half sine to the power 1x cos x plus a half times by I sub 0. Now this is even something easier to integrate, because I sub 0, well, that's going to be integrating sine to the power 0x, and anything to the power 0 is 1, so it's just integrating 1, so it just becomes x plus c, or just x. So let's try that and see what happens. So we've got I sub 4 is equal to negative a quarter sine cubed x cos x, then plus 3/4 of I sub 2, and I sub 2 we've got written here is equal to negative a half sine x cos x plus half of I sub 0, which is just x. Okay, and then that will give us this. I sub 4 equals negative a quarter sine cubed x cos x, then minus 3/8 sine x cos x plus a half times 3/4, so that's going to be 3/8 x. Now we could leave our answer like that, or if we wanted it all in terms of, well, not all in terms of sine or cos, but we may notice here, well, that's half the double angle for sine, isn't it? So this is half sine 2x. So what we could do then is replace this with half sine 2x. So an alternative solution would be that I sub 4 is negative a quarter sine cubed x cos x, and then minus 3/16 sine 2x plus 3/8 x. So either one of these two, this form here or this form here, would be fine as an answer. And actually we get this form here if we work out what sine squared x is. So if we work out sine squared x and we don't bother with this part here going down to I sub 0, then this is the solution you can get. But you can see, well, we can do it either way. Either work out I sub 2 and get this solution, or carry on till we get I sub 0 and get this solution. But you can see that they are equivalent solutions. Now we've been given an integral here, and we want to show that this reduction formula is true. Now this is different to the previous ones because we have limits. And just a reminder, when we've got integration by parts and we've got limits, then the integration by parts becomes this. If I've got my limits of a and b like this, so the uv part we apply the limits to directly, and then we also apply the limits to the integral that we work out here. So we just need to remember to do that in this question because of the limits. Right, so we have a product which is made up of two parts, x to the power n and root 1 minus x. So using integration by parts, we will have u equal to x to the power n and dv dx equal to square root of 1 minus x. We might want to write that as 1 minus x to the power a half. V will be n times by x to the power n minus 1, and v, well, we can integrate this. Let's just tidy up my square root sign there. Yeah, so this can be integrated using the reverse chain rule because the inside is linear. So we integrate the outside, which means adding 1 to the power and dividing by that new power. So that new power is 3 over 2. Dividing by 3 over 2 is the same as timesing by 2/3. The inside of the bracket doesn't change. And then we divide by the inside differentiated. So we're going to divide that by -1. So that basically becomes v equals -2/3 1 minus x to the power of 3 over 2. So I'll put this into the integration by parts, remembering that we have limits. So I sub n is going to be equal to uv with the limits applied. So that's -2/3 1 minus x to the power 3 over 2 times by x to the power n, and the limits are 0 and 1, minus the integral of du dx, or v du dx, and I've just realised I shouldn't have put v there. That should be du dx. So v du dx, that will be -2/3 1 minus x to the power 3 over 2 times by n times by x to the power n minus 1 dx. And I'll just add in the limits of 0 and 1 there as well. Okay, so the first thing we're going to do is to put the limits into here. Now if I put 1 into this expression, this becomes 0, so the whole thing becomes 0. If I then put 0 into this expression, this becomes 0, so the whole thing becomes 0. So that first part, when I substitute the limits in, I just end up with 0. Then what we'll do over here is we'll bring the constants over. So that will be plus 2/3 n, n is also a constant, and then 1 minus x to the power 3 over 2, and that's going to get times by x to the power n minus 1. And we'll just put these limits here as well. Now we really want this to be in terms of in minus 1. So we really want this part here written to look like this, but x to the power n minus 1 square root 1 minus x. So you've got that here, but this doesn't quite work. But this is the same as 1 minus x to the power half, or square root of x, times by 1 minus x. So if we write that in this form, maybe that will help us. So we've got I sub n equals, we don't need to write the 0, 2/3 n times by the integral from 0 to 1 of, and let's write this now as xn minus 1 times by square root 1 minus x, and that times by 1 minus x dx. And then what we can do is we can multiply these brackets to get two integrals. So we'll time this all by 1, and let's subtract all of this times by x. So that is going to look like this: 2/3 n. I'll just put this in brackets because I'm going to have two integrals here. So all of this times by 1, which will be this, x to the n root 1 minus x. Then minus all of this times by x Now if I times it by x, then this becomes x to the power n. So it becomes xn square root 1 minus x. Now you can probably see what's happened here. This integral here is I sub n minus 1, and this integral here is I sub n. So now we can make those substitutions. So we'll have I sub n equals 2/3 n times by I sub n minus 1, and then minus 2/3 n times by I sub n. We'll put the in terms both on the same side, so we'll have in plus 2/3 n in equals 2/3 n I sub n minus 1. We'll factorise the left hand side, so we'll get I sub n is and then in brackets 1 plus 2/3 n equals the 2/3 n I sub n minus 1. We'll divide both sides by 2/3 n. Yep, divide both sides by 1 plus 2/3 n. So 1 plus 2/3 n I sub n minus 1. And then what we'll do with this fraction here is if we times the top and the bottom by 3, and I think we get the required form. So in equals 2/3 times by 3 is 2n. Then 1 times by 3, 2/3 times by 3, 2n, and that equals, or that's times by I sub n minus 1. So we've got the form as required. I suppose the only difference is we've got the 2 and the 3 the other way round. That's fine. So I'll just say as required. Right, on this question here, this is the integral here, but it actually tells us how to write it, how to split it up here, and it also tells us which identities to use to help us to do that. Right, so let's take their advice then, and let's take our integral tan to the power nx dx and write it as they suggested. So that will be the integral of tan n to the minus 2x times by tan squared x. And then it also says by using this identity here. So that means I can replace that tan squared with sec squared x minus 1. So let's do that. So we'll get I sub n is tan to the power n minus 2x times by sec squared x minus 1. Now we'll expand the brackets, and that will give us the integral of tan to the power n minus 2x times by sec squared x. And then it will give us, I'll put the dx in just yet, minus 1 times by that tan to the power n minus 2x. Now we'll split the integrals up. So we'll get this, in is actually the integral of this, tan n minus 2x sec squared x. Now the integral of tan to the power n minus 2, well, that's just going to be I sub n minus 2 if we compare it with the original integral. So we'll do that next. So I sub n is this integral, and I suppose this is the bit we actually need to integrate and work out what it's going to be. So we'll have a look at that in a moment. Minus I sub n minus 2. Now what we've got here is a multiple, a product, where we've got one thing differentiated over here, but to a power. So sec squared integrated is tan. So we've got something that follows this type of pattern. You may recognize this from Pure 2. So we've got f dash of x times by f of x to a power n. And hopefully remember, if we've got something like that, then its integral is always going to be f of x to the power n plus 1 over n plus 1. So that's what we're going to use. It's one of those patterns, standard patterns. We call it the reverse chain Warner book. I prefer to call it using patterns. And yeah, that's what we're going to use here. So what happens then is this is going to be, this is the function, this is its derivative here. So it'll be like tan x to the power n plus 1. So if you add 1 to that, that becomes tan to the power n minus 1. Tan to the power n minus 1 over the power plus 1, and that's going to be n minus 1. Let's just put the correct term there, not tan minus 1, tan n minus 1 minus I n minus 2. Actually, now we're done. Now we could write this, I suppose, as I sub n minus 1, but they want it in this form with tan to the power n minus 1. So we can just put in equals, and we'll just move the tan to the side, n minus 1 minus I n minus 1 as required. Okay, so in this question it says we need to consider this integral here and prove this result. But we proved this result without the limits in example 2. So you might want to have a look back at example 2. But I'm just going to write it here. So without limits, this is the statement that we proved, that if I sub n is equal to the integral of sine to the power n x dx, then I sub n is equal to negative 1 over n sine to the power n minus 1 x cos x plus n minus 1 over n I sub n minus 2. So we prove this result without limits in example 2. Well, what do we want to do? We want to apply that result with limits. So if I stuck some limits on here, a and b, well then what happens to all of this down here? Well, the bit that we have sort of on its own, this part here, we need to apply limits to that, a and b, and then this, well, we'll apply limits to this integral here. So all we're going to do is take this result and apply limits to it, which we can do. Right, so we have I sub n is equal to the integral between 0 and pi over 2 of sine n, not sine squared, sine to the power n x dx. Right, so using the result in that red box there, or red bubble, we'll have negative 1 over n sine to the power n minus 1 x cos x between the limits of 0 and pi over 2 plus n minus 1 over n times by the integral of I sub n minus 2. Now that will be the integral of sine to the power n minus 2 x dx between the limits of 0 and pi over 2. Okay, let's see what happens then. Well, if we sub pi over 2 into this, straight away cos pi over 2 is 0, so that just becomes 0, minus, well, if we put 0 into this, we'll have sine 0 to a power. Well, it doesn't matter what the power is, sine 0 is 0, so that will end up as 0. So all of that will end up as 0. Then we have this here, so this doesn't change. But what you might notice is that this thing here is the same as this, but it's n minus 2. So this actually, all of this part here, including the limits, is the same as I sub n minus 2. So what we'll get is I n equals n minus 1 over n times by I sub n minus 2. Now all we need to do is to times both sides by n, and we get n times by I sub n equals n minus 1 times by I sub n minus 2, which is the result what we wanted, so we can just say as required. So let's move on to part B. In part B, we want to find these values here. 1 is sine to the power 5, 1 is sine to the power 6. So we will use this result, which we prove from part A. Right, so if it's sine to the power 5, it's I sub 5 we want to find using this. And actually what I'm going to do is I'll divide both sides by n. And actually then I get back to this. So really, I'm not going to be using that. I'm going to be using this. If I divide both sides by by n. Right, so I sub 5 will equal 5 minus 1, so 4 over 5, 4/5 of I3. Right, can we work out I3? So I3 is going to equal n minus 1 over n, 2/3 I1. Now can we work out I1? Yes we can. I1 is basically going to be the integral between 0 and pi over 2 of sine to the power 1 x. So what is that going to be? Well, if we integrate sine, we get negative cos between the limits of 0 and pi over 2. Cos of pi over 2 is going to be 0. And then we subtract the cos of 0, which is 1, so minus negative 1, so we'll get a value of 1. So that's the value of I1. So we can go back and we can say that I5 is equal to 4/5 of I3. I3 is 2/3 of I1, which is 1. And then what we've got to do is multiply that out. So we'll get I5 is equal to 8 over 15. So there's my answer to the first part of part B. The second part of part B isn't much different. We're just starting with I6 because it's to the power 6. So I6 is equal to 5/6 of I4. Okay, well, what's I4? Well, I4 will be 3/4 of I2. Okay, well, what's I2? We could probably work out I2 because that's sine squared. Let's make it even easier for ourselves. I2 is going to be a half of I0. Now I0 is going to be very easy to work out because that's the integral between 0 and pi over 2 of sine to the power 0, which is 1. Okay, so that's going to be x between 0 and pi over 2. So if we make the substitution, we'll just get pi over 2 minus 0, so we'll just get pi over 2. Okay, so we can finish this off and say that I6 is 5/6 of I4. I4 is 3/4 of I2, and I2 is a half of I0, and I0 is pi over 2. So you can see how easy this is. It's just multiplying. So I6 is 5/6 of I4. I4 is 3/4 of I2. I2 is a half of I1. So if we multiply all of that out, we will get, let's see, 15 pi over, and this is where my mental maths needs to work, 24 times by 2, which is 48. 48 times by 2, which is 96. Now I think we can simplify that. If we divide both of those by 3, we will get 5 pi over 96 divided by 3, 32. So there's our answer for the second part of part B. Okay, so this question here, this is the integral here, and then we need to show that this is true. I'm just going to write down one or two little hints that will be useful in this question. So one of them is a hyperbolic identity, which is that tan squared x is equal to 1 minus sec squared x. Another one, you'll find it in the differentiation section of the formula book, but if you use it backwards, it will tell you that when you integrate sec, you get tan. Okay, that's using the differentiation table in the formula book backwards. Another hint for this question is when we see integral of this form, where you see the derivative and the function itself to a power, then we know that becomes the function to one higher power over that one higher power. And one other thing for this question which is going to be useful, and that is the definition of tan x, which is e to the 2x minus 1 over e to the 2x plus 1. So even though we're not told any of these things in this question, we will need all four of these to help us answer this part. Okay, so let's go through and we'll see how they're going to be useful. So we have our integral between 0 and log 2 is tan to the power nx. Now we don't have a product here, but we're going to split it up into a product. This is very similar to example 4. Now what are we going to split this up into? What are the two powers going to be? Well, there's a little clue down here. Can you see this? N minus 2. So we're going to split this up. So we have log, or the integral between log x and 0 of tan n minus 2x times by tan squared x. Okay, right, and now we use our first hint here, is that we're going to change this to 1 minus sec squared. So this will be tan n minus 2x, that's going to be times by 1 minus sec squared x. Next thing we're going to do is we're going to expand these brackets. So if we do that, between 0 and log x, we'll get tan n minus 2x minus tan n minus 2x times by sec squared x. Right, now this part here, let's put a little bubble around it. So that part we can replace with I sub n minus 2. So now the question becomes I sub n minus 2, that's the first integral, minus this integral, and that is the tan n minus 2x times by sec squared x. Now this is where we use the third hint here and the second hint, because this part here, I could think of that as my f dash of x, and this part here I could think of my f of x to the power n minus 2. So it fits this pattern here, this integration pattern here, so we can use this to integrate this. And also I know that tan differentiated, if I use it backwards, is going to be Scheck squared. So that's my relationship between the two. Right, so now we can move on and we can actually work out what that integral is going to be. Okay, so minus, and between the limits of log 2, was it log 2? Oh, I noticed that at some point along the question my log 2 has been changed to log x. So let's change all of those back. Log 2, not concentrating, there we go. Right, yeah, so now we'll have tan or tanh to the power n plus 1. So we add 1 to this power here. So that becomes n minus 1 over that new power n minus 1 and limits and log 2. Now we want to evaluate this, and this where we use this hint here. So we'll actually put these values in for tan checks. So we'll make that substitution and we can put the limits in. So now we'll replace tan with its definition. So I'll have this. And I'm also going to take this n minus 1 outside of these brackets, otherwise we're going to have like fractions over fractions. So if I write minus 1 over n minus 1, and then that just gives me a bit more space to use this definition here, and that will be e to the 2x minus 1 over e to the 2x plus 1. Now all of this is to the power n minus 1, and we need to substitute in those limits of log 2 and 0. So here you can see that I've actually written it out. I've substituted in the limits. If I substitute in the log 2, this is what this becomes. Then I subtract with the limit 0 substituted in. Now this will become e to the power 0, which is 1, so it becomes 1 minus 1, 0. This will also become e to the power 0, which is 1, and 1 plus 1 is 2, so effectively that's 0. So this is what we're left with. Now we can use the rules of logs, because 2 log 2, let's write it here, is the same as log 2 squared, which is log 4. So effectively you can write this as e to the log 4, and the e and the log will cancel out, just leaving you with 4. So e to log 2 is actually equal to 4. Right, so what am I going to have? At the top I'll have 4 minus 1, so let's just write this out. So we have in, our integral is equal to I sub n minus 2 minus 1 over n minus 1 times by, well, this is going to be 4 minus 1, which is 3, over 4 plus 1, which is 5, all to the power n minus 1. And you can see that we've proved this as required. I sub n minus 2 minus 1 over n minus 1, 3/5 n minus 1, so we can just put as required. Okay, now for part B, I've put a couple of hints up. Well, actually that's what we proved in part A, so we may need that. And also we'll need the integral for tanh, which is in the formula book, which is log cosh. Now cosh, definition for cosh is e to the x plus e to the minus x over 2. So you could say that the integral for tanh x is log this. Okay, so that if we have a look at this question, it says that we want to show that this equals log 5 over 4. Now you might look at that and think, well, you know, how does what we've done link? But there are some similarities. I've got this 3/5, but instead of n minus 1, I've got 2r, so maybe I can make a substitution, and maybe I can rearrange this first so that I've just got this part here, or something that looks like it. So yeah, if I take what I proved in part A and rearranged it, I'll get this, that I sub n minus 2 minus I sub n is equal to 1 over n minus 1 3/5 to the power n minus 1. Now what I'm going to do is I'm going to replace n minus 1 with 2r. So I now get this, I sub, now remember what I'm doing is I'm replacing all of these n's, whoops, let's highlight that, all of these n's here, here, here and here. I'm replacing them, or the n minus 1 I'm replacing with 2r. Now this n minus 2 here, well, that could be written as n minus 1 minus 1, so that gives me the n minus 1 to substitute, and the n that we have here, well, this could be written as n minus 1 plus 1. So I'm just writing it away where I can make those substitutions and replace n minus 1 with 2r. So I will have I sub 2r minus 1 minus I sub 2r plus 1, and that will equal to 1 over 2r times by 3/5 to the power 2r. So now what you'll notice is now this looks exactly the same as this here, apart from the sum. So now we'll have that part, the sum of 1 to infinity. So the sum from r equals 1 to infinity of 1 over 2r 3/5 to the power 2r, well, that's the same as, so this to the sum of from 1 to infinity is going to be the same as this to the sum of 1 to infinity. So r equals 1 to infinity of I sub 2r minus 1 minus I sub 2r plus 1. Right, now I don't think we're going to have to write out an infinite number of terms and sum them up. That will take a long time. In fact, it'll take an infinite amount of time. There must be some way in which they cancel out. So let's see what happens. Let's start with r equals to 1. So when r equals to 1, this will be 2 times 1 minus 1. I'll have I sub 1 minus I sub 2 times 1 plus 1 are I3. And I want to add to that what I get when r is 2. So when r is 2, I will get I sub 3, 2 times 2 minus 1, minus I sub 5. Then I want to add the next one when r is 3. So that'll be I sub 5, 5 minus I sub 7. You might see what's going on here. There's going to be some cancelling out, right? Now we'll go all the way down. Let's say to r equals, let's not use n because we've used n before. Let's use a different, let's use m. So when we get to r equals m, and we're going to be adding this as well. Now that will be I sub 2m minus 1 minus I sub 2m plus 1. Now method of differences. Can you see that if I've got minus I sub 3 and I'm adding that, those are going to cancel out. Those are going to cancel out. The cancelling out pattern goes like this diagonally. So they will cancel out like this. So the I7 will cancel out. And it's going to keep cancelling out all the way down until that one gets cancelled out there. then the only terms we're going to be left with are I1 and minus this one here. Now you could write this term here, since we're going from r equals 1 to infinity, suppose we could say, right, this is I sub infinity, couldn't we? We could write it like that. We're looking at the limit as m approaches infinity. So then let's do this. Okay, so we'll say as m tends to infinity, what we'll get is this. That sum will equal I sub 1 minus I sub infinity. Now I sub infinity, well, that's going to be what we get when we have this, so tanh, and we're going to have that. That's not the proper notation, but you get the idea that when we get to this infinity term, n is going to be approaching infinity, and we're told in the question that basically this is equal to 0. So this sum that we're trying to work out from r equals 1 to infinity of this 1 over 2r, 3/5 2 to the power r, is going to be this I sub 1 basically minus 0, or basically just I sub 1. So what is I sub 1? Well, that's this. It's just tanh to the power 1 dx. Right, now we can go back up to these hints up here. What do we get when we integrate that? Well, we get log cosh. So it's going to be log cosh between 0 and log 2. Let's put the 2 in. Right, we know the definition for cosh, so it will be the natural log of e to the x plus e to the minus x over 2 between the limits of 0 and log 2. Okay, so now we can finish this question off. So if we put the limits in and we put in log 2 first of all, then this will just become 2, and this will become a half, because you can move the negative over there, so it's 2 to the power negative 1, so e to the power log 2 to negative 1, it just becomes a half, so you get 2 plus a half over 2. When we substitute 0 in, then we'll get 1 here, we'll get 1 here, so 1 plus 1, 2 over 2 is 1, and we've got log 1, log 1 is 0, and then 2 plus a half is 5 over 2, divided by 2 is 5 over 4, so we end up with that log 5 over 4 as required. Okay, so we've been given this integral here with no limits. It's been called I sub n, and it says by considering this, so this is a starting point for us because we may not know where to start, show that this statement here is true. Okay, so let's work that out. Let's work out what is I sub n plus 2 minus I sub n. What's that actually going to be? Well, it's going to be integral of sine, and we'll replace n with n plus 2, like this, over sine x minus, let's put tx here, minus the integral of sine nx over sine x dx. Okay, that's step number 1. Now, I would have a look at this and say, right, these are over the same denominator, so let's put that all as one integration. So we would get next sine of n plus 2x minus sine nx all over sine x. So that would be my second step here. Now there is a way of quickly simplifying this, and it's using this, that sine A minus sine B is equal to 2 cos and A plus B over 2, I'll run out of space here, times by sine a plus b over 2. That's a quick way of getting the answer, because we could replace a with this n plus 2 times by x and b with nx, but you may not necessarily be thinking that way in an exam. You may not necessarily recognize, oh yes, sine a minus sine b, and then remember this from the formula book. You may do, but you may not. So I'm going to go through the method that you didn't remember this expression here in the formula book, and let's say you saw this and you were working from this bit here. Now what would we do? Well, I would be looking at that and say, well, this bit here, let's multiply it out, and then I'll be thinking of the addition rule for sine. So let's multiply it out. So I've got sine nx plus 2x minus sine nx all over sine x, and then I'd be thinking to myself, right, let's use sine a plus b here and expand that. Right, so that would be sine nx cos 2x plus cos nx sine 2x minus sine nx all over sine x, like this. Then the next step I might be thinking to myself is, right, okay, let's factorize this, because I've got a sine nx and a sine nx there. Let's factorize it and see what we get. So if I take sine nx here, then in the brackets I will have cos 2x minus 1, and then plus cos nx sine 2x all over sine x, like this. Then next I'll be thinking about double angles. Yeah, I'd be thinking about replacing this here with, let's say, 1 minus 2 sine squared x, because then the 1 here and that negative 1, they would cancel out. And I'd also be looking at the sine 2x here and thinking, right, let's replace this with 2 sine x cos x. Now, as I said, using this would be quicker, but if you don't think that way, you might be thinking this way. Let's see how this goes and see what we get next if we replace those double angles. So over here, as I said, in the brackets we'll just be left with negative 2 sine squared x. So I could write it as negative 2 sine nx sine squared x. If I then multiply the brackets, and then I'll have plus 2 cos nx sine x cos x. Now, by doing this, every term now has got a sine x in it, and then I can cancel them down. So I can cancel down sine here and sine here, and that sine squared will just become sine. So I'll be left with this in my next step. So negative 2 sine nx sine x plus 2 cos nx cos x. Oh, and it's not over anything because we've just divided or cancelled down by sine, so we can write it like this. Now you may or may not recognize what's going on here. We have, if I write this the other way around and put the sine first and the cos here, we've got the addition for cos. We have got a cos, let's see, would it be plus? Yeah, a cos a plus b here. Yeah, I'll write it the other way around so that you can see and move the 2 across. So I'll have 2 over here, and this can be written as cos nx cos x minus sine nx sine x. And this is the same as cos nx plus x. Now if we write it like this, cos and then in brackets the n plus 1 times by x, yeah, we can see that we can easily integrate that by using the reverse chain rule. Okay, so we're going to integrate the outside, so that means cos becomes sine. The inside of the bracket doesn't change, so we'll keep it as n plus 1 times by x, and we divide by the inside differentiated, so the inside of that differentiator is going to be n plus 1. Now remember, ages ago what we said is that this is actually I sub n plus 2 minus I sub n is equal to what we've just written there. Okay, so 2 over n plus 1 times by this sine n plus 1 times by x. I need another set of brackets there, like that. So we can add I sub n to both sides, and we end up with I sub n plus 2 is equal to 2 over n plus 1 times by sine of n plus 1 times by x plus I sub n as required. Now, if you did remember this expression and use it, then you would get to this answer here much more quickly. It'll probably only take you about another 3 steps of working, 3 to 4 steps of working. But not everybody's going to be thinking that way and remember this from the formula book. And if you don't, it can still be done, but it's going to take you a few minutes longer to get the solution. Okay, we're on to part B here, and we want to show that the value of this, exact value of this, is this here. So this would equate to I sub 6, wouldn't it? Yeah, with n equals 6. So that's what we want to find, I sub 6. So I sub 6, using the recurrence relation here, how do we find I sub 6? Well, I sub 6 would be when n is 4. So I'll just write that down, n equal to 4. So we just substitute 4 in, not 6. So that'll be 2 sine, and then it will be 4 plus 1, 5x over 5 plus I4. So now we want to work out what I sub 4 is. Well, we'll get I sub 4 when n is 2. So we want to substitute 2 in. So that will be 2 sine 3x over 3 plus I2. Right, so we want to find out what I2 is. So I2 would be what we get when we sub in n equals 0. So that would be 2 sine x over 1 plus I0. Now, to find I0, we're not going to use the recurrence relation again because you'd have to make n negative 2. So we use this here, yeah, to find I sub 0. So I sub 0, we can work this out directly, would be the integral of sine 0x over sine x. Now we've got limits of pi over 3 and pi over 4, so we can evaluate this. So what's going to happen here, we basically got, doesn't matter what the value of x is, we're going to end up with sine 0. So we'll end up with 0 between the limits of pi over 3 and pi over 4. So it's just 0. So we've got now the value of I0. We can now work backwards Okay, so, or forwards. So I6 is equal to 2 sine 5x over 5 plus I4. Now what's I4? 2 sine 3x over 3 plus I2. And what's I2? 2 sine x over 1 plus I0. And what's I0? It's 0. Now since we've got limits, we just need to substitute our limits in here, pi over 3 and pi over 4. Okay, so basically what I've written down here is what we get when we substitute the limits in. Now since we want an exact value, if we just type this in on a calculator, we may not get an exact value. So it's probably best to calculate these separately. Okay, so if you work out each of these values separately on your calculator, these are the values that you get. And then if we type this on our calculator, we actually get 12 root 3 minus 17 root 2 over 15, which is what we were asked for up here. So we can just say as required. We're going to do exercise 6a on pages 194 to 197. So just a quick recap. Reduction formulae is a recurrence relation used to solve integrations where repeated application of a single process is used. For example, integration by parts. So here's an example of where we might see that. In these questions, you may be using a trig identity or a hyperbolic identity. We've seen the examples that often we look for this pattern to be able to find an integration for it. And any questions where you have limits, don't forget to use the limits.